Hello all, today we are covering 6.1, roots and radical expressions. It's really just a continuation of the previous video. So you guys will be able to find nth roots here. So, the first thing we have here is a fraction in our exponent. Now that looks a little weird to have a fraction exponent. It is totally valid to have it like that. And you can rewrite that fraction exponent as in the nth root of a to the first power. I like to say that this is saying power over root here. So when you write this in this new form, not with a fraction, but with a root, you put the denominator on the outside of the root and the numerator or the power on the inside. Okay? So we have that power over root idea. Let's go ahead and try some of these. We are going to simplify the following, meaning turn this into a root and then simplify that root. So we have power over root here. We have power and then we have the root. So we want to do the root on the outside and the power on the inside. The power of 1 does not change what this number is, so that's kind of just extra information. It's all good though. We just need to take the cubed root of negative 216. Now, if it was a square root, a fourth root, a sixth root, anything like that, having a negative inside would make us have an imaginary, but any odd root, that is totally fine. You can have a negative inside of your cubed root and still have a non-imaginary solution. So, to find the cubed root, you can go ahead and see if it's actually a perfect cube with a calculator. It turns out it will be. Or if you don't want to check using a calculator or don't have a calculator available to you, just find all the prime numbers that go into this. So we have 2, negative 2 I will say, and then 108, and then keep going, 2 and 54, and 2 and 27, and then 3 and 9, and 3 and 3. Now, notice you can then highlight the leaves, the ends of each of these, and that is equivalent to the cubed root of negative 216 when we write these out. So 2 times 2 times 2 times 3 times 3 times 3. Now notice we are looking for groups of 3s, so I group these up, a group of 3 2s and a group of 3 3s. Like yesterday, if there's a negative, that just makes this whole group become negative. They come out front, these come out front. This actually means this is a perfect cube. You'll notice over here the 6th one, so 1, 2, 3, 4, 5, 6. So the cubed root of 216 is actually just 6. But because it was the cubed root of negative 216, our solution is then negative 6. And we're done. We have our solution there. We can do the same thing with the next one. The only real difference between yesterday's and today's is that we now have our exponent as a fraction, which then we can now make for this one, for example, the fourth root of 81 because we have power over root. The power of 1 doesn't change anything. So we are just finding the 4th root of 81. We can go ahead and split this out. Say 9 and 9. 9s both go to 3 and 3. So we've already found our leaves for our prime factor tree. So this 4th root of 81 is equivalent to 3 times 3 times 3 times 3. We can go ahead and group these because we need a group of 4 this time because we're talking the 4th root. These all come out, and the solution to this is actually just 3. The 4th root of 81 is 3. So that is a perfect 4th root. And then the next one, we need to do the 5th root of negative 32. Once again, that is totally fine because it is an odd number root. So the 5th root of negative 32, split it out to 2 and 16, and then 2 and 8, and then 2 and 4, and then 2 and 2. So we can finish by highlighting our leaves, primes there. And this is then equivalent to the 5th root of 2 times 2 times 2 times 2 times 2, because we have 5 2's shown here. We do need a group of 5 numbers. We do have that group of 5 2's. Once again, this 32 is a perfect 5th root because there is no leftover numbers inside the radical, and we have our solution. Okay? Hopefully that's not too bad for you. You can try some of those out on your own time. Now we are going to rewrite expressions. This time you'll notice we don't just have a 1 in the numerator like we had above, but we have a number m. Maybe a 1 sometimes. But for these examples, we will have a different number other than 1. So you can rewrite these expressions using what we learned on the intro to lesson 6, or chapter 6. So if we have power to a power, we know that we would multiply those powers together, meaning we can separate them out like so. So if you were to multiply m to the 1n, 1 over n power, that would get us back to the original. So that is totally valid to split them out like that. And then this looks like what we had above right here. So now we'll just replace that with power over root, the nth root of a to the 1, but the 1 doesn't change anything, all to the m power. And then if our fraction exponent is negative, we start out by flipping the whole thing. You don't just flip the fraction actually stays as is. You just put the whole term in the denominator, and that makes the fraction happy, okay? Now from here, this part matches this, so we can finish it out the same way. It's just all in the denominator now. Now this is a completely valid way to do it. I'm going to show you the way I like to do it as well as this way, just so you can choose which way you like better. So we are going to start with A, evaluate the following expressions. You'll notice this is like the first expression rewrite. You can leave the base 16 and the denominator now with a 1 on top, all to what the numerator was. This is still equivalent. Now you can take and make this the root that it needs to be. So 16 to the 1/2 is the same thing as saying the square root of 16, still all to the 3rd power. Then you take the square root of 16 inside the parentheses and you get 4 to the 3rd power. And when you take 4 times 4 times 4, you end up getting 64. So that is following the rewriting expressions model above. The way I like to do it is I like to say, okay, so we have a to the power over root. That is the same thing as saying power over root here. We wrote this above. Okay, so where you see the power in the fraction exponent, you put it inside the radical with the base, and where you see the root goes outside. Now, if it is a denominator of 2, that's just a square root. We don't usually put a 2 out there. Okay, so this next one I am going to, actually, let's do A the way I like to do it, and then we'll go from there, okay? Actually, I just had it written out there. We'll do A the way I like to do it. So, I see this 16 to the 3 over 2 power. I know 16 power over root, so square root of 16 to the 3rd power. I take and I simplify inside the root. So 16 to the 3rd power is actually 4,096. And I know that needs to be square rooted because that square is in my denominator. I take the square root of that number just to check to see maybe it is a perfect square. Turns out it is. We get 64. Notice these do match up. Good thing they do because they should get us the same answer. All right. Now part B, I am going to do the rewriting expressions way, and then part C I will do my way. Okay, so part B, notice we do have this guy down here. I am going to go ahead and put all of this in the denominator. The fraction stays the same, but it all becomes happy down there. Okay, now I'm going to follow through the steps. I'm going to keep my base. The denominator of my fraction stays while the numerator is 1, and then I pull out the numerator multiplying by that. It is a power to a power, so it's still equivalent if you were to put it back the way it was originally. And then we go ahead and we write this as the 5th root of 32 all cubed. Now I'm going to take the 5th root of 32. I know I saw it just above. Maybe you didn't remember that when we split these out, we could do the factor tree, or you could just know what your 5th roots are. I will say I don't just have my 5th roots memorized, but maybe you do. We know that there are 5 2's, which means we needed a pair of 5 something to reduce it. This means that the 5th root of 32 is a perfect 5th root, and it is 2. So now we have 1 over 2 cubed, which just leaves us with 1 over 8. Simple enough. On this last one, I'm going to show you my way, the power over root way. So we have 4 to the 5th power root 2, which we don't write a 2 out here because we know just a square root is the second one. Now I take the 4 to the 5th power, that's just 4 times 4 times 4 times 4 times 4. That is equal to 1,024. Now we have to take that squared. If this is not a perfect square, we just have to simplify it like we did on the previous lesson. Thankfully, though, this is a perfect square. We just get our solution is 2 by the calculator. Sorry, the solution is 32 by the calculator. And we're good to go. Now in Math Excel, it's going to ask you to put these back in exponent form. So it'll give you something like this blue cubed root of 343. Probably not with that 1 there, actually. And it wants you to put it back in exponent form. So this is still your power over your root idea. So you go 343 power over root 1/3. And then it'll ask you to finish out this problem. So you just take and solve it out and finish and get your number. Okay? All right, now example 3, we're going to simplify the radical expressions. This is really quite similar. We just now are looking for groups of numbers as well as letters. So I think the easiest way to do this is to do a bunch of writing. I can forego doing that on my numbers if I already know what the perfect squares are, like those two are perfect squares. I can skip that part. I can know that that's part of my answer. The square root of 16 is 4, and just write out all my letters. So this is really just saying x multiplied by itself 8 times. I think that's 8. 2, 3, 4, 5, 6, 7, 8. Yep. And I am looking for pairs of 2 because it is a square root. So I'm going to highlight my pairs of 2. You'll notice there are 4 pairs of 2, which means I now bring out 1, 2, 3, 4 x's, and nothing is left on the inside. So I now have x times x times x times x as my reduction. So my final answer is actually 4x to the 4th based on that. Okay? You can also use a different idea. We'll get to that in just a minute. Here you can do the same thing. If you know the square root of 81 is 9, you'll know that's part of your final answer. And then you can list out your x's. So we have 4 of them, x times x times x times x. If you're taking the square root of those, once again, we need groups of 2. We have 2 groups of 2, so that's just going to bring out 2 x's. So we have x times x, or x squared. Okay? And then on this next one, here's the other way you can do it. You can either list them all out like we have been, look for pairs. But there's a lot of them, right? That would get kind of crazy to write out so many things. They would be super long. So instead of doing that and looking for pairs, you will get the same thing as if you simply divide the exponent by the root number. Okay? Oh, we're looking for pairs of 4, not pairs of 2. My bad. Pairs of 4. 1, 2, 3, 4. 1, 2, 3, 4. There we go. That's better. So if you have x to the second here, you'll see that we had 2 groups of 4 x's. Those all come out. There's nothing left on the inside. So you would then guess that you would have y to the 3rd because 12 divided by 4 is y. If we wrote out all those y's, so we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We have 3 pairs of y's that come out, so we have y to the 3rd, and we are good to go there. So if you prefer to divide the exponents like that versus writing them all out and finding groups, either way is totally valid. Choose what works best for you. And then lastly, same thing here. You can decide to write them all out, or you can simply decide to just divide by the root number here. Just your exponents though. And if it comes out even, you have a to the second, b to the third. If it doesn't come out even, then you'll have some leftover, like say just a single a inside. But because it comes out perfect, we have a to the second, b to the third as our solution. Okay, last thing. Say this time we are finding the fourth root of x to the 20th, y to the 28th. Something special happens when you have an even root, such as 4, 2, 6. And we will see what that happens here. I also missed it on part C, so we'll take a look at that one. We have to edit it a little bit. So, even root, like this one, and we'll go ahead and solve here. We can either write out 20x's and 28y's, or you can just go ahead and divide those powers by our root number. If they come out nicely, like 20 divided by 4 is 5, and 28 divided by 4 is 7, we are good to go there, okay? Now, the thing that we need to watch out for when we have even roots and when we get odd powers is the fact that even roots could produce imaginary solutions. And if we have odd powers in here, we could still have negative numbers under our radical. So to eliminate the possibility of that happening, we just put these answers within absolute values, making sure that those have to be positive, okay? So I missed that on part C, but the same thing happened. We had an even root, and we got one of these being an odd power. So the term with the odd power should also be in imaginaries. So watch out for that. Or sorry, the term being with the odd power should be in absolute values because we could get imaginaries otherwise. All right, and that's all I have for you. Have a great afternoon.